In the previous lessons, we saw that the engine efficiency depends on the degree of cylinder filling with the mixture. With more air intake during the first stroke, we have higher output power, torque, and lower fuel consumption. It is necessary to find possibilities that would provide better filling of the cylinders to improve the engine efficiency. There are several ways to better cylinder filling. In this lesson, you can find out which methods are used and how to cylinder charging during air intake. Dynamic supercharging. The amount of power and torque is determined by the percentage of fresh air in the cylinder during intake. The load level is the volume coefficient of utilization. It is defined as the ratio of the actual and theoretical amount of filling in the engine cylinder. When the engine during the first stroke has no obstacles to the air intake, the cylinder filling level represents a theoretical quantity, and the volumetric coefficient is 1. For example, this is achieved when the cylinder head is removed, and the air can freely occupy the entire internal space of the cylinder. The air pressure inside the cylinder is equal to the atmospheric pressure. However, in reality, there are obstacles to air suction during the suction stroke. The filter, throttle, and intake valve restriction on the cylinder head slows down the cylinder filling. All this reduces the amount of air intake, and the actual volume coefficient is less than 1. These attenuations represent pumping losses. The engine must use part of the generated mechanical energy to overcome losses and suck in air in a smaller amount than the theoretical one. All this is reflected in the reduction of power and torque of the engine with increased fuel consumption. So, naturally aspirated engines have lower efficiency due to lower volume coefficient. The volumetric coefficient can be increased by applying a supercharging system. In that manner, more air can be placed in the combustion chamber compared to a naturally aspirated engine without superchargers. In naturally aspirated engines, the volumetric coefficient ranges from 0.7 to 0.9. While in supercharged engines it is greater than 1 and amounts to 1.2 to 1.6. The advantages of supercharged engines are more engine power and torque, higher engine efficiency, lower fuel consumption, reduced exhaust gas emissions. There is a limit to the increase in volume coefficient in petrol engines. If there is too much pressure inside the cylinder, self-ignition of the mixture may occur before the spark appears. This can damage the pistons and engine bearings. That is why the system for filling petrol engines is carefully designed so as not to exceed the maximum volume coefficient that can lead to damage to the engine. There are two different systems of engine superchargers: dynamic chargers and independent chargers. Dynamic chargers use some natural physical phenomena that under certain conditions can increase cylinder charging. During the suction stroke, the air flows at high speed through the suction line and has a kinetic energy. This movement is maintained as long as the intake valve is open. At the time of valve closing due to compression, the pressure at the end of the intake manifold increases, which leads to the rejection and movement of air in the opposite direction at the speed of sound. The return wave at the beginning of the intake manifold hits the stationary outside air, which leads to a change in the direction of movement towards the engine cylinders. If this wave returns at the time of opening the next intake valve, there is a sudden penetration of air into the engine cylinder, pulling the outside air. In this way, more charge is obtained because it takes place from the movement of air. Depending on the shape of the intake manifold, we have two different dynamic supercharging systems: variable length intake manifold and resonance pulse intake manifold. Both systems can be combined to create a mixed dynamic charging system. Variable length intake manifold uses the effect of oscillating air movement through the intake manifold while the intake valves are closed. At lower engine speeds, the time between two intake valve openings is longer. Therefore, the intake manifold of a small cross-section is needed to allow the return air movement time to coincide with the opening of the valve. Also, due to the slower movement of the piston, the intake valve is open longer, the cylinder filling time is extended, and the intake line is used with a smaller section. At higher engine speeds, the time between two consecutive valve openings is shorter. A shorter suction line is then required. Due to the faster movement of the piston, the intake manifold of a larger cross-section is used to deliver a larger amount of air to fill the cylinder in a shorter time. So, to use the effect of oscillating air movement, a longer and narrower intake manifold should be used for lower engine speeds and a shorter and wider one for higher engine speeds. Longer and shorter intake lines are combined on vehicles. Depending on engine speeds, the switch valve redirects the air into one of these two intake manifolds. The ECU closes and opens the valve based on the engine speed. The control can be done via a vacuum valve or a stepper motor. For example, when the engine speed is less than 4,100 revolutions per minute, the diverter valve is closed, and the air goes through the longer intake manifold. When the engine speed is above 4,100 revolutions per minute, the switch valve is opened, and the air is sucked in through a shorter path. It can be seen from the graphic that the engine with a variable length intake manifold is more efficient and that in the area of the average engine speed, it has a significantly higher torque compared to the same naturally aspirated engine. The second type is dynamic chargers that use the resonance pulse charging effect. Resonance is an enhanced natural oscillation of an oscillating body. It occurs when the frequency of the external force coincides with the natural frequency of the body on which it acts, causing maximum oscillations. When the opening time of the intake valves coincides with air oscillations in the intake manifold, resonant charging occurs. It is known that large masses cause low frequencies, that is, long pulses. That's why resonant chambers are added to the intake manifold, increasing the air mass to obtain long air pulses that coincide with lower revolutions per minute and longer time intervals between two valve openings. When these two intervals overlap, there is a resonant enhanced pulse of the air and a resonant filling of the cylinder. On some vehicles, unusual side boxes and pipes without connections can be seen on the intake manifold as resonance chambers to boost charging at lower engine speeds. Some engines combine these two dynamic chargers. In this way, you get charging in a wider range because you get the best out of both systems. Thus, resonant charging is used at lower engine speeds and with variable length intake manifold at higher engine speeds. In the example of a 6-cylinder engine, the folding valve separates the intake line of the first 3 cylinders from the other 3. At middle speed from 2300 to 4500 revolutions per minute, the valve is closed. When, for example, the intake valve of the first cylinder is open, the second part of the intake line serves as a resonance chamber. In this way, the air mass increases, which reduces the frequency of the vibrating mass and adjusts to the valve opening frequency. When the intake valve from the second group is opened, the first part of the intake line is the resonance chamber. When the engine speed is above 4,800 revolutions per minute, the folding valve opens, and we have dynamic supercharging with a variable length intake manifold. It can be seen from the graph that the torque has increased significantly in a broader range of engine speeds, especially at higher ones. In this way, by applying natural physical phenomena, better charging is achieved, and a more efficient engine is obtained with lower fuel consumption. Dynamic superchargers are present on engines, but they are unnoticeable and little known. The variable length intake manifold engines have coiled intake pipes above the engine that look like ram's horns, as many call this system. You can recognize the resonance pulse intake manifold by the additional resonant boxes and tubes on the intake manifold. Now you know about them and you can easily spot them under the vehicle hood. Their role in the injection system is more clear to you. Also, you know there are valves on the intake manifold to divert the intake air and operate the dynamic superchargers.